Hi guys, this is the first edition of Rust Live, which is part of the live series here at Amicus Recruitment. So today we're kicking things off with a special webinar, and we are joined by Bastian Gruber, who is a senior software engineer who specialises in Rust development. So today he'll be giving us a talk about asynchronous Rust. So if anybody wants to leave any questions throughout the webinar, then they can use the comment section in the tab. But what we'll do is we'll save any of them for the end when Sebastian's finished. So it should last around 30 to 45 minutes. But yeah, we'll do the questions at the end. But Sebastian, yeah, I'll hand over to you.
Okay, thank you. Starting with sharing my screen. I hope you can see the screen now. Yeah,
I think we're good to go.
Okay, perfect. Cool. So yeah, welcome and thank you for joining the webinar. So I will present who I am and what the webinar is about in the first few slides. And then we take it away. So that's the first one in the Rust series. So the goal for this next 30-45 minutes is for people curious about the language, for people who work with Rust but just used it maybe just in an synchronous way, get a feel for how to write it in an asynchronous way and how to go about it. So after the talk, you should feel very confident in when to use it, how to use it, and where to look further if you have any questions. And so my name is Bastian Gruber. I'm a software engineer for about 15 years now. I'm working with Rust professionally for about 3 years, and I'm currently working in a very asynchronous environment and in sort of distributed, with distributed systems in Rust. And a part of the content for this webinar is taken out of my book. It's called Rust Web Development. So if you're more curious about how to use these techniques more for a web environment, how to create APIs, how to use web servers in Rust, this is the book for you. So some of the content, some of the graphics are out of the book, but some different code snippets are also taken out of the GitHub repositories of the crates I'm presenting, or I'm taking the snippets out. So as mentioned in the beginning, the goal is, since the topic about asynchronous code is quite deep, and I want to make it short and precise and you feel good afterwards, I decided to go a bit in depth, but also a bit wide, so that you actually have something practically to use afterwards. So after this whole 45 minutes, you should know certain patterns, how to start multiple parts of your asynchronous code at the same time. You want to contribute to a library. I show some code patterns you might find there, and I present different crates on how to get started in the ecosystem. And especially if you come from a language like Node.js, or a framework like Node.js, or a language like Go or Python, you should get a feel of what's different in Rust and why is it so different, and the reasons behind it, because it's quite important to not just to compare the both, but and just see, oh, I have to think a bit more in Rust. It's important to know why and how much more you have to think about it in Rust. So I really hope that after this webinar you have a really good grasp about it. So this should be for both Rust developers, but also sort of newbies in Rust. I won't explain much of the Rust syntax, but I just point out the asynchronous bits. But it's not too complex just to follow. And to get started, we have to ask first, what is asynchronous code? And to define some terms to know what we are dealing with. If we want to look further, so you have the right terms for Googling or to ask ChatGPT if you want to know more about it. And the terms which are oftentimes used in this environment is parallel, concurrent or concurrency, and asynchronous. And these three terms mean very different things. And when we talk about parallelism, it's like when you have like one or like more than one CPU, so that you can split the work between different CPUs and also start to like work on different tasks actually at the same time. So like each CPU can make work on your task, like let's say calculating some complex numbers, crunching some complex numbers, like it takes a lot of time and you want to maybe start to do this work in parallel and like run it like at night or at the weekend. And when we talk about concurrency, this usually means that your operating system or your CPUs are faking parallelism. So like it means that you want to start multiple tasks at the same time, but the CPU or the operating system decides to pause in between. It can be that you are like waiting for an HTTP response, and in this time, there's not really much more to do than waiting. So then you can give the operating system or the CPU the chance to do something else while you wait. So like it's sort of like moving the mouse pointer and watching like a YouTube video and listening to an audio stream. Like it seems like you're doing this all in a parallel. It might be, but it might also be that you have little nanoseconds of pauses in between these tasks. So like concurrency could mean you just have one CPU, but you still want to start to work on multiple tasks at the same time. And like when we talk about asynchronous code, it means that the language you're using to facilitate parallelism or concurrency, that the language offers you the chance to write your code so you can start like work in parallel. So like the asynchronous part is just like a language feature and has like nothing to do sort of like with the core computer science concept of doing multiple things at the same time. And this might take something forward, but like since this is a talk like which should cover like a broader like range of topics, and for you to afterwards know what to look out for, you really have to know like when to use what. Like when do you want to use parallelism and when to use concurrency. And I mentioned it in the previous slide. You want to do like a parallel type of work if the work you want to start work in parallel if the work is CPU bound. And this means that the processor has lots of work to do, like lots of calculations. Crunching numbers is like one example. Like you want to calculate an average or you calculate prime numbers or I don't know what, but this is usually heavy for the CPU. And to be faster, you split this work between different CPUs. If you have like mostly IO bound work, which means reading files, this could be like a web server who is getting multiple thousands of requests per minute, and then which has database read writes in there. This type of work is usually like waiting. You're usually like waiting for an HTTP response. You're like waiting maybe for a file to be able to be like read. You're like waiting for a database query to finish. And this IO bound like work, like the CPU is not really fully like engaged all the time. And then it doesn't really matter to, it could be, but like it's not not really like the core like advantage to have like multiple CPUs be started or being in use. You want like a concurrency paradigm where you give the operating system the chance to wait for certain things. So in the background, you can, I don't know, like accept more HTTP requests and start more database queries. So like the parallel type of work is CPU bound work, and the concurrency like work is IO bound. So like, and this is like important for then like which environment and how your like Rust code will like look like. And like a nod to the book, it's like if you are like creating web servers, you have to know that it's mostly IO bound work. So, and the standard in the industry is sometimes just to have like a multi-threaded, multiple CPU type of environment. But it could be that you split up like the reading to sockets on multiple CPUs. It's not really a speed advantage. Just to have this in the back of your mind. It depends highly on the like environment you're operating in, but like web servers, for example, are highly IO bound because like you're mostly like waiting for stuff to happen in the background. And when it comes to Rust, now the question is, how can Rust facilitate this type of work? Or how does a language or like a mechanism usually look like? And we need 4 core abstractions or features. You usually need a syntax. As we mentioned, asynchronous code is a language feature. So we need the language to be able to say this block of code is an asynchronous block of code. So like mark it as such. So the compiler knows like what to produce to hand it over in the right type to the CPU. You need special types, like in Node.js, this will be like a promise. So you need a more complex type, which can store a type of process, because you sometimes start to fetch a file, or you want to read a file, or you want to query like a database, which might take some more time. So you want to store this in the type, like it's not really just an integer. You want something which tells you I'm not really done working on this type of work. Check back every few seconds and I will tell you like once I'm done. And you need some sort of threads. So this piece of work you want to store. So like once the CPU or like the operating system goes back to this type of work, or like it can pause it and say, this database query now takes a while, I do something else in between, but it wants to go back to this piece of work and see, are you done yet? So, and this is usually means like a thread. And what modern languages do is having these types of threads in like the user space. You could technically use operating system threads, but this is more expensive since you constantly have to use system calls into the kernel to create and read these threads. So a term which is used in the industry is a green thread, which means they just live in like the user space. So you need some form of asynchronous runtime, which can facilitate this piece of work. And also, if we talk about asynchronous code, if you, for example, run on top of like the Linux kernel, you want to make use of the asynchronous kernel API. And there also needs to be an abstraction. For example, I know like Node.js has like C++ like abstractions on it, on top of it. So for like Rust, you also need something on top of it. So like how this building blocks filled out look like, actually the Rust language just gives us the top 2 in the standard library. You have the syntax, so you can mark an asynchronous function as async, and inside of it you can await on a type of like work. so that your compiler like knows this might take some time and I want to use a thread for this and I want to be able to like work on it in the background. And you also need a type. In Node.js, this would be like a promise. In Rust, this type is a future. It's not really a type that's a trait you can implement on top of a type, and we see like the trait in the next slide. But this is where it stops. Rust pre 0.1 had a runtime built in, but that is cited against it because like Rust wants to be a systems programming language first. So then the question was, if you want to have a runtime which can create threads in the user space, you still want to be able for the programmers to create threads in the kernel too. And then you have two types of creating threads, and this might get confusing. And this is just like a small piece, like why they decided to not to include a runtime in the standard library. And you need the asynchronous kernel like abstraction, and the standard in the ecosystem is a crate called Mio, which provides this communication layer like with the kernel. So if you work with Rust, you basically have to like include a runtime, and each runtime already has like the Mio crate integrated. And how it looks like, we will see in a second. So, and this depends of how much you actually do asynchronous code and in which capacity. So if you are an application developer, you might not implement this trait. You might get a type future back, and then you can await on this future, but you might like never implement this future trait by hand. If you are like a crate author, you might want to get familiar like with this crate, because then this gives the users of your crate the possibility to use your crate in an asynchronous way. And this is how it looks like. Like it has a poll function, which can tell you, yes, I'm done like with my work, or it tells you, no, like I'm not done. And the runtime you are using is calling this poll function on a future to make work on this future. So like whenever the runtime decides, yes, I want to continue to work on this. So let's say this could be like a database query, and the runtime like would call poll, and then you have a type which could be like an integer or like whatever type this future might give back. So in the Rust ecosystem, you probably find 95% of the time that crates and applications are using the Tokyo runtime. And this was like both like Mio, the kernel abstraction, is integrated or is getting shipped with Tokyo. And Tokyo, it's interesting to know, by design is creating like a thread pool, and they check for your local CPU, and they will create one thread per CPU by default. So you have to know if you want this, and we talked about this in the beginning, if you want to have parallelism or concurrency, sort of like what is the impact of this design decision. This might not be like a negative impact, but this might also be that in your like use case, having like multiple threads or have one thread per CPU might not necessarily increase your speed of your operations, just to have this in mind. And to finally to see some code after all this hype, and this is basically like one line, which is like all of these like runtime and kernel like abstractions. If you want to use, if you come from Go or from Python or from Java, to write asynchronous code in Rust, you have to include Tokyo in your cargo toml, and then you have to annotate your main function with like the runtime name. So it's Tokyo. And you also have to tell your main function that this is an asynchronous function. So and then you can use .await inside of it. And that's sort of like your starting point in writing asynchronous Rust code with all the background you just heard. And for example, in this short example, it obviously doesn't make sense if you just have one HTTP call. You can also do it synchronously, since there's not a second or third heavy task you want to do in the background. But just like a short example, which fits on one slide, is you have the main, or like you have the runtime annotation on top of your main function. You tell your main function that this is an asynchronous function, and then inside of it, you can use .await. So then like and we are using a third-party crate here, which is called request. And this crate gives you the option to run it in an asynchronous way. Here, just with one, doesn't make much sense. But if you have hundreds of these requests, it's quite helpful. So here you have .await to make this GET request, and then to form out of this GET request like a JSON, or like to parse JSON out and store it in a hash map. This is also done in an asynchronous way, because the JSON could be quite large, like what you get back, and then you call again .await. And what happens behind the scenes here, you have here this HTTP request, so like you write this, and what then the compiler and like what's happening behind the scenes is you mark it as an asynchronous function. The request crate will give you back a future, and the future will be like used by the Tokyo runtime to actually start the future, to make work on the future. So then like the runtime decides when to like work on it. Like it will pass it down this HTTP request. It will use the asynchronous API from the kernel, tell the kernel, please make this HTTP request. The kernel will do so, will get an answer back. So, and while you get an answer back, now you could do something else. In this case, you don't, you just wait. And then it goes back up, and Tokyo has a reactor executor like model, which basically the reactor is calling, for example, epoll from the kernel, and the kernel says, hey, here comes, or like, here is your HTTP request being done. Here's the result. And then the executor will like wake up the function or like your thread again, fill out your future type with the result, and then pass it back to your application. And this would be sort of, like the same thing as like a sequence diagram. So I think it's quite important to know that if you write asynchronous code, you have the runtime hidden behind the scenes doing the work on your future. This is why you need a runtime, and Rust doesn't have a runtime. So just to have this in mind. So some more examples of like what you might come across. Because we use now Tokyo as our like example runtime, and there are more. You can see that you could use, for example, like the file module from the standard library, but here we use like the Tokyo one, which means we use the asynchronous way of creating a file. And again, here it's just like one file creation. So like it doesn't make sense to write this in an asynchronous way. But you can imagine that you start, for example, the HTTP request, and like while this is happening, you start to create a file to be able to store the answer from the request. And how this might look like, we will see in the design patterns section of the talk. So here, like that's important to know that if you want to use Tokyo, you also then will use their abstractions over the standard library. So instead of using stdd file, system file, you use Tokyo fs file. And also then like the copy to the file has that .await too. How this might look like in how to create a server, it's the same here. We have our main function, and you can also see that we like the root function is also an asynchronous function, which I think Exam dictates that it has to be one. Here, like we basically just give back like a static string, so like it doesn't really need to be an asynchronous function. And so this would be like the interplay. So if you want to start a web server, like a web server project in Rust, you have to include the crate or like the web framework, and in this example, this would be Axum, but you also always have to include Tokyo. Even if Axum tells you we are based on Tokyo and you have to use Tokyo, you still in your cargo toml have to do both. You have to like include Axum and you have to include Tokyo, so you can do this annotation on top of main. So to summarize it, we need like a type and we need the language features. This is like the future trait in Rust and the async await keywords. But then to actually make like work on this type of future, we need a runtime, which can create the screen threads, which can talk to the kernel. And this most of the time is Tokyo, and I show 2 more of these types of runtimes in the end of the webinar. And sometimes it's also important to know, like this was asynchronous code, and these were the types of things you need to write asynchronous code with. But now you have threads. Now you might have to start 10 different HTTP calls and you wait for all the answers. And now it's the question, wait, but how do you actually share data between these threads? And Rust makes sure that like with the ownership like model, that before you compile your application, that without needing a garbage collector, that all of this data is thread safe. And you have these types of primitives in different languages as well. But in like Rust with the ownership model, you have to think maybe sometimes a little about why you use certain types to share data or state between your threads. And these are the typical 4 things you use, which are channels, which is to have like a one-shot channel or like an open channel you can have between, and then you can send data to this channel, and each thread can then like listen to the channel and read the data. And we show an example right after the slide. You have a read and write log because you can share state between those threads, but you want to make sure that not 2 threads at the same time are like manipulating data. So you need some form of like mutex or a read write log to make sure that if a thread wants to change or like manipulate data, that it can request a log, it can use this to write some data. If another thread at the same time wants to manipulate this data, it knows to wait. And after it's freed again from the other thread, it can also do this. And you have something called like an like an arc, like an atomically reference counted pointer. This sounds super fancy, and we will see like how this interplays with a read-write log in 2 slides. And you also have atomics, which we won't get into this like webinar, because I think it's it's not a niche use case, but it might not come across in your first few like years too much. So, but just so you know, these 4 things are sort of synchronization primitives and have nothing really to do with asynchronous code writing. So like we go to the first one, and Tokyo, also the runtime we chose, has like a primitive called a channel. So as you can see here, and we didn't talk about like the spawn yet, and we will do so afterwards in like the design pattern, but with Tokyo spawn, you basically create a new thread. So here we create 2 new threads. But before we do this, we create a new channel with a size of 32, so that we make sure we can't overflow this channel and use all like the RAM we have. And we also have to, so like what you find most often if you like work in an asynchronous Rust way, you have to move the ownership into this closure. So here you see, after opening the channel, we have like a receiver and a sender, and like we want to move the X part into the closure of this first thread, and we want to own it, and therefore we clone it. So now we have 2. This might also be able like without a clone, but this async move means that this closure takes ownership over it, and then we can send a message. We send the message in the second thread, and then we can check for the channel for the incoming like messages, and we can see now that both threads can communicate with this channel. And you find this pattern a lot if you work with different crates. If you work in an asynchronous Rust project, that you will see this type of Tokyo spawn, which is creating like a new thread or a new task. In Tokyo terms, you take over the ownership, like with the move, like you move the ownership into the closure, and then you can use this channel inside the closure. And now to this long here, like where the atomically reference counted pointer and the read-write log, you would use this, for example, if you have an in-memory storage in like a web server, for example, and you want to share state between different route handlers, you will have this combination of an arc and a read-write log. And what an arc does is it's creating, like, instead of cloning, like each time this list of like the users, you will create this once in your memory, and then an arc makes sure that each time you clone this list, it will just increment the counter. So like Rust does not have a garbage collection, so it wants to make sure if no other function is using this type of like memory or like this storage in memory, it wants to be able to delete it, and to drop it. But it has to know how many threads or processes are currently using this in-memory storage. And therefore, like if you clone this arc and pass it on to the next route handler, this clone will just increase the counter. And then the read-write log is there so that like multiple route handlers can't mutate this list in memory at the same time. So you can imagine that you have a route handler to delete some users or to update some of the users, and you want to make sure that just one process at the same time can mutate the memory. So this combination you will find quite often, and like most of the time they come in pairs. And you see like the spawn here again, that we basically each time like we call like the lookup like the users, we basically start them at the same time. And like we start a new task on the Tokyo runtime. And so for more, because there are 3 more patterns or sort of like mechanisms you will come across or you might want to use, and I call them patterns. Like the first one is like, what do you like in case, for example, you want to start a server like an API, but you also at the same time want to maybe connect to a database, make an HTTP or an RPC call to set up like the database or to fetch some informations, and you want to start, or like you might have 10 different HTTP calls with each start of like the service you want to call, and you want to make sure to all start them at the same time. So in like Rust terms or in Tokyo terms, you would use the join macro, which would start these asynchronous functions at the same time. So like you might start a server, you fetch something from another place, like from an external API, and then in your main, you say, like, once you start this, please make sure to start all of it at the same time. And this you would do with Tokyo join. Sort of like you start them sort of in parallel, but then it depends on your CPU. Tokyo might decide to start them on different threads, but Tokyo might also decide to start them on a single thread. This is basically up for Tokyo to decide. But this you would find quite a lot. And we already saw the spawn, and the spawn will create a new task or a thread, like task in Tokyo terms, and it will put this task on like the Tokyo thread pool, and then Tokyo can decide which thread will make work on these futures. And like with web servers, we saw it in in the past, like each incoming request, as we said previously, it's most of the time IO work. So you might want to update a user in the database. This means this route handler now has to wait until the database is updated. So in the handle request, you could spawn a new task, so that you know that Tokyo will be able to move this task on the background and can do like more things, like while it waits for this task to be done. So now Tokyo can start to do like the work. So like it calls the handle request will start a new thread, and then Tokyo will come into the foreground again and can like accept a new request. If this would be written in like a synchronous blocking way, then if the handle request would have to fetch 2 million entries from a database, and this might take a minute. In this minute, this server here wouldn't be able to like accept new requests, because then Tokyo, or like then your application like would basically block your one thread, and then like the kernel has to wait until your application is like available again, and then it takes in like the next request. So in like web servers, it's quite common, or I think it's standard to do this in this way. And you also have a select, and the select is most of the time when you listen on different sockets or channels and you want to, like once one type of work is done, you want to drop all the rest. So let's say you have like multiple, like you listen on like multiple sockets and you're like waiting for a new incoming request. And you want to tell your application as soon as the first like message comes through to like one of the channels or to one of the sockets, drop like the rest of like the futures, and I want to use this to make work. So this could be like a design pattern to shut down a server. So this can be that you always receive like an incoming request through a channel. This takes some time. This might take a minute or like a few like nanoseconds. But once you send like a shutdown like message, this will be handled right away. So then your application through the select macro says, hey, shut down now and drop all the other open sockets or like the futures. If this is clear, like it's hard to communicate this through a slide. But if you see this in a crate or you join a Rust project, know that like a select means as soon as one message comes in, drop the work on the other open channels and just use the latest finished message. This also has a downside where you have to know if you like write a future by hand and someone is using one select, you might have like work which is started, but the calling application will just drop it. So then you might have inconsistent data state, but this is just an advanced use case, I guess. So yeah, now you've seen it. Maybe you can ask me a question about this after the webinar, or I will try to find a better example for you, like of how to use it. So now to come close to the end of it, now you've seen of how like Rust is like using it, and you might wonder, well, then why would you use like Rust if this is so maybe cumbersome to use, and why not just like Node.js, where you might think, oh, this all like works just by magic and it always like works fine. And one of the reasons is the Rust compiler makes sure that like with all these like message passing and data passing, that this is actually thread safe, that the Rust compiler makes sure that there are no data races. It makes sure to use the right like mutex or the read-write log, so actually just one thread can manipulate the data. So like the compiler helps you if you ever want to write this type of code by hand, that this code will be thread safe. And for example here, you might think, okay, like I start a channel, I create this arc like with a read-write log, and I pass it down to this, like how you say, to this closure, like I create a new thread, like I pass this arc down, like I unwrap it, and like I send like a message out, like this must work, right? And the thing is, no, it's actually not, because like the Rust compiler tells you that the sender can't be shared safely between threads. And this is sort of like a longer explanation, and I put a link here because I couldn't like explain it better than the write-up did. But it's just nice to know that that a Rust compiler has your back. If you might not be so familiar with channels and read-write logs, you probably can be 98% sure that in your use cases that the Rust compiler will tell you if you have like a mistake in there. And TLDR, like the too long didn't read, like version of this problem is that you should use a mutex instead of a read-write log in this example. And why and how? Feel free, like it would blow up this talk here. Feel free to read this in the blog post. And now we talked about the different type of work, parallel, concurrency. We talked about Tokyo. And so now, like, the advantages that Rust doesn't ship a runtime by default. You as the application developer now you have a choice to choose a runtime which fits your actual processing needs. So by default, you would use Tokyo because it's just so well supported. It's super solid. Bigger companies like AWS are using it. So if you find like a web framework crate in Rust, chances are very high that they will build on top of the Tokyo runtime. But a Tokyo runtime is very good in IO bound work. This concurrency type of work. If you have a CPU bound work, which means you use Rust for machine learning, for example, and you have to compute 1 million data points and you want to do it as parallel as possible, you would use a runtime called Rayon. And you can Google it, like I didn't put a name here or like a link here. And this crate, and is also mentioned by the Tokyo runtime, this is the preferred way of doing parallel type of work with Rust. And you also have Glomio, which is a bit more like advanced, and your use case might be able to profit from it. But they basically say that for like most of the stuff you might not need Tokyo. It is probably faster to use Glomio because they do like a thread per core design, and they use like the kernel like abstraction IO uring, which in some cases this might speed up your work. So they say if you have a standard, for example, like a chat server, and you would by default maybe use Tokyo, and then Tokyo in this case would maybe not be even faster than in a synchronous way, sort of. And so like they describe it like well, and they link a blog post to it. So I would encourage you to look into Glomio just to understand some of the design decisions in like the Rust world. And the last few slides now, just to wrap it up. Now, after hearing all of this, is like it's quite a lot to take in, to learn, to consider. I actually don't think it's so much different than to write like Node.js code. It gives you the advantage of to actually writing more performant asynchronous code, but you have to like consider more things. And now the question is, well, then why would you use even like Rust for a web server, or why would you use like Rust for like machine learning? And the answer is basically because like Rust is the only language which is highly used out there and doesn't have an active garbage collection or an active runtime during the runtime over the application. So you have in this diagram that Go has an active runtime which will be compiled and sort of like run with your source code. You have Java like with the JVM, and like Node.js has sort of like a runtime cost like with the complexity of V8. And the only language you can compare Rust to is C and C++, which are like the lightweight or like the most lightweight version of a compiled code. But like Rust gives you the speed of C and C++, but it also makes sure that before you compile it, that your code is thread safe. It doesn't have an active garbage collection. So you get both things, like you get the best stuff from like Node.js, with a caveat, you have to think maybe 10% more about your code, but you also get the speed of C, which works super well for like web servers, for growing your applications. It might even like make sense a lot in like machine learning. So this is quite beautiful. So like you don't have an active garbage collection during runtime. Your code will be compiled into like a state machine in the end. And yeah, like so like the summary is, yes, you have to think a little bit more, but I think I covered probably 80% of the cases in this last 50 minutes now. So you can look up those different topics, patterns. So I think the overhead for the programmer is not so much. You have to learn a little bit more to use it better, but then you will gain all the advantages afterwards. Yeah, that's the end. So thank you for joining. And if we run out of time for the questions, feel free to shoot me an email. The email I didn't put in is foreach@me.com. Feel free to ask me, and I will make sure to follow up. Thanks.
Okay, great. So yeah, for anybody that's got any questions after this, please feel free to reach out to Sebastian. Just mentioned his email there, but you know, if you're happy with them dropping your connection or message on LinkedIn, then yeah, please do. For anybody that's looking for new opportunities within the Rust space, then please give me a message. I'm more than happy to assist you with that. But this webinar has also been recorded, so if there's anything that you would or you think that you've missed or you need to reference back to, then it will be available this week on our YouTube channel. But yeah, Sebastian, I don't think is there anything else that you'd like to add? Or
yeah, just in general, reach out. I think it's like worthwhile. I struggled for the first few months in getting or in wrapping my head around this. It can take some time, but the payoff is just huge. So it's worth to dig deeper. And again, if you want to write web servers in Rust, like or APIs, feel free to pick my book. There are a few free like example chapters out there, and I think this really helps you to speed up some of your like microservices, or it will also get you as a software engineer in more interesting type of work with this language. So I think the payoff is huge. Okay, great. Well, yeah, thank you everyone for joining us. Hope this was useful and that you can implement it in your current or future projects. But yeah, keep your eyes open for our next Rust related events. Sebastian, thank you for today. Yeah, thank you for attending. And thank you for hosting this. Yeah, but okay, sorry for interrupting you there. But no. Yeah, no, that's it from me. But yeah, everyone, thank you for joining, and yeah, goodbye. Bye.